actually in a modern topic, as we will see, that I believe there has been no silo yet, which is bordering the topic of unlearning, right? So throughout the world, there are a lot of frameworks and laws that aim to protect the privacy of citizens in the modern era, right? So the European Union's GDPR framework is one of these frameworks, and is probably the strictest one that exists right now in the world. And it has a lot of provisions for protecting citizens of European Union countries against their data being used online and how. And specifically, there is Article 17 of this GDPR that is called the right to erasure or right to be forgotten, which, as highlighted, it mentions that the controller, think of this as the company who trains the model, can oblige or should oblige to deleting personal information without undue delay, right? So basically, for machine learning, this means they must delete the training data upon request. And following this is rather important. Why? If not anything else, it is important because there are a lot of legal battles ongoing the last few years in European Union on this, with major firms like Google facing fines of hundreds of millions of dollars throughout the European Union, right? So Spain with Google, Amazon with Brussels central headquarters, Apple with France. And these are just some of the battles that are related to Article 17, right? If you search for GDPR alone, there are billions of dollars of fines through pretty much every big tech firm out there. And there are many more battles ongoing, which means that these stakeholders that train these large models, they need to comply with some very serious online privacy rules, right? So complying with this is one thing, but the problem is that many of these large models that we have nowadays have been trained already, and therefore deleting the data is not a problem for them. But how do you retrain an LLM that costs $1 billion when someone requests that you delete the data? Sure, you delete the data, but how do you remove also the effects of this data from your models, right? If we had a convex model, it would be way, way easier. But now with these LLMs and all these backbone models that we have and the ways we're training them, deleting the effects of that training data gets a little bit trickier, right? So let's see how this would go in a regular training, right? So we have a company with dataset D, and this company just uses the whole data set. It trains the model usually with a gradient-based algorithm. And now someone requests some of the data to be deleted, which you can see in red, right? Now, in principle, what happens is that the company has trained the model. So that is our assumption throughout the talk, that the company has already trained a model. And now they need to comply with GDPR and delete the effects of that data also from their trained model, which are pretty expensive. So we have the red set denoted as DX, which I'm going to mention as forget set in this talk. And we have the green set, which is essentially the rest of the data that we haven't received any requests, so we can use for training. Right, so the company trained with all of the data because this request came after it had trained the model. And now the model needs, in principle, to retrain the model with just the green data to obtain the final model. The problem is retraining is expensive, right? Company has to face a legal battle or retraining a model that costs billions of dollars. And imagine that these requests are not coming all at once, right? Citizens can keep on requesting this for their own reasons at any point. So this would get very, very expensive. And as you can see in the graph, training of a neural network is generally getting more expensive. Besides, there is progress with GPUs and TPUs, but we're always pushing for bigger models, right? So retraining is not the great idea, and this is where machine learning enters the chat. So machine learning is an idea that has been emerging the last few last few years, and has the following very simple concept. Can I fine-tune with one way such that the model that I output is equivalent to me doing the training from scratch only on the allowed data? Again, the D with the log that comes in green is called the retain set. And these are the allowable data, right? We haven't received any request to exclude that data, so we can train at those with no problem. The issue is that privacy-preserving methods like differential privacy do not focus on this, and this might cause an issue, and new algorithms are necessary. And of course, where there is demand for an algorithm, there are some researchers who are willing to push that boundary. And there is a lot of work in the literature from major universities across the world and also Google, to spearhead and make progress with this topic of machine learning. And this is very well framed in the NeurIPS 2023 challenge, mainly organized by Google, that received an unusual amount of registrations for a NeurIPS challenge, thousands of registrations with close to 2,000 submissions, right? And this was only for a NeurIPS challenge. They have very interesting insights that you can visit in the webpage and find out more, but essentially many interesting ideas started coming out of there, right? So let's see now a little bit more formally, how does this look like? So we have a training data set where we have the samples xi and the labels yi, and we have a pre-trained model F trained on all of the data, right? And then some instances are requested to be removed, and these will be called the forget set and denoted in red. And the rest, if we take out this data to remove, will be called the retain set, right? So essentially the goal of machine learning can be summarized in 3 criteria. We want essentially to forget the data that are requested to be removed. We want to retain the performance, right? And we want this to be done efficiently, like everything in machine learning, as cheap as possible. And this creates a lot of interesting trade-offs. And the naive solution, if we remove any of these conditions, can be very simple, right? So if I remove the condition 2, of course, I can just predict at random. But altogether, they create quite an interesting framework. And again, there are a lot of works, but just to present one of them very briefly. So this is a 2-page summary of, essentially 2-slide summary of one of these popular works out there that do unlearning. So the idea was that you trained a teacher model where the teacher model was trained with all the data, forget set and retain set. And now through distillation, once you receive what is the forget data, you can train a student model that basically needs to agree with the retain set data. So have high accuracy, for instance, if we're talking about recognition on the retain set, and disagree on the forget set. And the key idea here in this particular paper is that they're going to do this with minimizing the KL divergence between the original model with the parameters WO and the unlearned model. And specifically, the objective that they are trying to optimize for is that they have these three terms. The first one is that you stay close to the retained set. To further solidify this, they have the second loss term, which is essentially task loss on the retained set. So for instance, if we're talking about image recognition, make the accuracy be high, for instance, cross-entropy loss. And the third one, which is a gradient ascent step, which essentially means moving away from the forget set. This particular idea was, of course, something inspired by the GAN literature, for those of you that have been around and know what this is. Yeah. Yeah.
Is this some sort of generative model, I guess? Or this is just a softmax? What do you mean by the probability?
So this is generally can be in any model, but this particular paper is focusing on essentially, and most of unlearning is focusing at the moment on discriminative tasks, so recognition. Yeah.
If it was binary,
Mm-hmm.
disagreeing is agreeing in some way. Like, because you basically say, you say yes, I say no, but it's like somehow there's still that strong pattern to it. I mean, what does that term mean?
Complementary, yeah. So binary classification is one of these problematic cases, but usually, and I will actually mention in a few slides one motivation in the binary classification, but for most cases, you're not assuming binary classification. Like, so think of missed classification, right? So like I have 10 digits and yes. So like
uniform.
You're way very advanced, thinking several steps ahead, Rob, Vikas. Yeah, but the concept here is that you don't need to do this over that many epochs as your original, like this is a fine-tuning step, right? So we assumed and we started off saying that we have a pre-trained model that costs millions, hundreds of millions, we don't care. But we are, like, this is not the objective for training the model from random Gaussian initialization. This is training, like fine-tuning an already pre-trained model. And in fact, you are not wrong saying that like this is equivalent to at some point doing some training of the model. Yes, you could completely cause a distribution shift on the way, and essentially almost retrain the model, but we're just using it for a few epochs to fine-tune. Great questions. And one of the problems with unlearning, I said machine learning has been raising, but then there is this quite interesting paper from last year showing that even if you do apply a state-of-the-art machine learning algorithm, your prediction is the same as if you trained in the whole dataset, which means basically this is fine for examples in the retained set. This is what we wanted, but this is not fine in the examples in the forget set. It means we did something costly, fine-tuned, and yet our prediction remains almost the same as we had before. And they showed that, in fact, the claim is that the data that are in the support of the training distribution, which are the data in the forget set, the prediction remains most of the time the same.
Just to make sure. So you're saying basically they got rid of the problem at the sites of the data training set, but it's still extrapolating the new examples in the same way as the old, which is problematic because it means they'll learn how to extrapolate from the state. Is that what you're saying?
Not exactly, but this raises an interesting point, which took me a few months to also realize. In this problem, it's not like the typical problems, I guess, in machine learning that we're looking into. The forget set is part of the training set. So like basically when I say that like, so when I say here that this happens for the support of the training distribution. This means that it also happens for the forget data, right? So like, for instance, in this room, if we had each one a vote for a favorite color, and I ask my data to be deleted, and someone on the with management trains a model for me, for them to forget what I voted, but still that model would still classify my vote as the same, even without or with unlearning. So basically this here means that it's not changing after unlearning the vote that it should. And this is where I said that you are quite advanced. Let me present though one use case which makes it a little bit more clear, hopefully, right? So unlearning is effective and is a very active area of research with a lot of exciting results. But here is one case where it might get tricky, right? So as far as I know, all of these large models nowadays, not only LLMs, but all types of large models are trained on pretty much a compressed version of the internet, right? And the compressed version of the internet means Wikipedia, fine, medical history, financial data, criminal records, right? This is public data in the US, and court cases are public data in the US, which means that if a person P now has some corrupted record for whatever reason, if a model provider trains a model on that data, and that model costs a lot of money to be trained, and now some employer, or even worse, a law enforcement, picks that model and queries that model with the data of XP, the problem would be that this person would be classified as high risk with high probability. And if that person P invokes the right to be forgotten, then the company that trained the original model would need to provide some reasonable algorithm that can make the model be unlearned, right? The problem, as I mentioned, though, is that the prediction before and after unlearning is mostly the same, which means even after unlearning, when the employer or law enforcement queries the data of this person XP, that person would be still classified as high risk. And this essentially means that the person is not protected, even with unlearning. And you might say, okay, who cares about criminal records? We don't have one. Sure. Let's go to another example, financial fraud, right? So FTC reported billions of dollars lost in individual and institutional money across in 2024 alone, right? So again, we are training on both public and private data, and stakeholders like Bloomberg might be training on financial records that they have or obtained through the banks directly, right? These banks are selling the data. And imagine a person P, who is probably the unluckiest person on earth, has an identity theft, right? So someone steals their data. Of course, this person P might be totally honest, doing all transactions as they should, but the identity theft was done for malicious reason, right? So even if the person P complies and follows through, reports it to their bank, if the bank has sold that data and someone else or the bank itself trains with that model, then essentially any future financial discussion, prediction, for instance, if the person wants to take a mortgage, would classify this person as high risk with high probability, even after unlearning. And this is where Rob's point was probably 6 slides ahead. This is not something that we would like in the cases that we have corrupted or incorrect data, but it even gets worse, right? So far, we assumed everybody was honest and doing their best. But as we know in the ML literature, the last few years, there is something called adversarial attacks, where on top of everybody being honest, there is one adversary that can make things worse, right? So, for instance, here you can see the toy example of NIST that is classified with a network with probability is 0.8, right? Now, if someone runs a very, very simple attack inspired by projected gradient descent, and you can see the noise highlighted here, what happens is that the corrupted data can have even higher probability, right? Which means that now, not only we corrupted the data and we are able to get malicious results, we even make it less likely for the correct decision to happen. And interestingly, what would be a good way to solve this is maximizing uncertainty. And this is, again, back to Rob's comment, right? So this is, again, the same slide with one change, which is if now from the original model of high risk, I made one change that classifies high and low risk with equal probability, right? So if I increase the uncertainty over the prediction, then the mortgage lenders or any financial institution can no longer confidently classify that person as a high-risk person. Now, of course, the question is, how do I go from this original pre-trained model that someone did train, it still classifies the person as high risk despite having corrupted data, to this model? The person did invoke the right to be forgotten, and we need to go from this model to this model. So this is essentially the goal that we are setting in this new work, that we want to induce as close as possible to uniformity without retraining from scratch to defend against adversaries that do have model access. And let me pause here for a second. Why do we need model access? Any guesses? Stronger adversary, stronger statement, yeah. But what would be the why? Let me rephrase the question. If the adversary did not have access to the model, could the company get away with doing nothing? Yeah, the company could just have an if statement, right? If this person invokes it, change my decision arbitrarily, right? So they could just avoid being honest and doing their best to change the decision. And this is the simplest hack that I guess we would like to avoid. That's why we're imposing model access. Yes? Mm-hmm.
Would it necessarily ever trade that? I guess, like, what's the argument?
Yeah, that's an excellent question. And the answer to that is really tricky, because if we didn't have that person in the training set, then we wouldn't know in what area of that manifold, like high dimensional space, the representation would fall into. So we cannot just make it uniform, because by extension, that would mean making the whole space uniform, right? Which means that I wouldn't need to learn anything. I just can get the uniform prediction always, right, over the label set. But I think what we have done is possible for you, once that person requests their data to be deleted, for you to fine-tune, even if to fine-tune the specific area of representation, so that like basically their prediction becomes also uniform, even if their data was not in the training set. But this does require a minor extension to what I'm saying. But this is an excellent question.
Then talk about thinking about uniform.
Yeah. Yeah, excellent question. I mean, I can imagine and see where also on LLM, since it's a softmax software distribution, you can impose uniformity. But basically in this work, we focused exclusively on the discriminative setting and even more on images. Extending to the generative setting is an excellent question. And I think it's, we do have it in the future extensions of the paper. Just a second, Manoli, you had a question? Okay, let's go here and then. Sorry, could you repeat the last sentence because I didn't hear the last one? Mm-hmm. Sure, but that imposes a risk, right? So, like, imagine the law enforcement. They might say, yeah, this person requested their data to be deleted, but which way would they be classified? Sure, in the binary classification, as Rob was saying, it's clear that you might be classifying in one of the two ways, and just making it uniform doesn't solve the problem. But like, imagine when we have 100 possible classes, right? If I know it's almost uniform, which class am I going to predict, even if I do know that the person requested their data to be deleted? And in fact, in this threat model, so for those of you that are coming from the privacy, this is slightly different from the common privacy background where knowing that the person requested their data to be deleted might be a violation. Here, it's fine. We don't care if the law enforcement or anybody knows that the person P requested their data to be deleted because they can't predict confidently anyhow. Yeah?
To follow up on that, like, am I worried about somebody taking a model like this and searching for places where the prediction is finding those data points? Like, you know, the example. As to their information be needed, that would be like a stronger attack.
Yeah, that's something that we haven't done, but I guess it's possible. It's possible, yeah. If you could invert it, it's possible that you could retrieve some additional information, but we haven't gathered against that. Yeah, Nali.
Like to ask a question based on the story that you said about the federal government.
Mm-hmm.
So, first of all, this trigger, if all of the people that would require anonymity, then to follow that situation, you should uniform, it will destroy the.
Yes.
The federal government testing. That's one that use the company. It can be. Does the federal government that choose randomly?
No. The federal government is not training any model, so it's not choosing anything. Is the blue part is the company, right? So like think of this, for instance, for the case of financial data, Bloomberg or Google, right? So then individual people can request their data to be deleted, right?
The fraudulent activity.
Oh, no. The fraudulent activity is someone else that stole the data of the person, for instance, in this particular example. But you are correct, like if in principle, every single citizen on like a country requests the data to be deleted, then we don't need to train anything because we cannot train on anything useful anyway. But there are many cases where this is even on the public eye, right? So like some people here, I'm sure, have Wikipedia pages, right? And this is public. and I might request the data to be deleted. So like basically there are a lot of ways that, yeah, if everybody requests at the same time to be deleted, you can just predict uniform anyway. You don't need to spend millions learning. But in practice, I think the whole machine learning literature depends on the principle that very, very few people will go through the hoop and request the data to be deleted. Awesome. Okay, so how do we do this? It's not, so I spent quite some time in the motivation slide, but it's not that hard to imagine the simplest algorithm do, which is what we actually did, right? So again, we have the forget set denoted in red and the retain set denoted in green. And we can assume any retained loss over the parameters. For instance, think of this cross entropy for our experiments. And the additional thing that we're imposing is that we're imposing a uniform loss over the parameters, where the uniform loss is implemented as a KL. Vikas, to what you're saying, it's directly a KL between the softmax and the uniform distribution. And essentially, we call this Pareto fine-tuning, and this is how you would normally train a model, right? How we train most of the models. We minimize the loss in the pre-training step, and then in the fine-tuning step that we are doing for obtaining this maximum uncertainty, what we are doing is that we're balancing between this uniformity and obtaining high accuracy in the rest of the retained set. And to balance these two, to interpolate between these two, we introduce a parameter theta that balances this. And in all the paper, I mean, here I'm not presenting really much of the theoretical results that we do have in the paper, but for all the theoretical analysis, we're assuming that our weights are bounded by C. And essentially, we have a typical weight regularization and L2 regularization on both the pre-training and the fine-tuning steps. And with these simple things, how can we choose theta? Well, if we assume now an additional step, which is that the first loss that we want high accuracy is the cross-entropy loss, then our objective is to minimize this distance. What does this say? This says that essentially our model, when invoked on the forget set, is as close as possible to the uniform prediction. And how do we characterize this? The infinity norm, which means in the worst case, it should be less than epsilon. And with those, you can choose essentially some theta that is bounded by the ratio that you can see on the screen, and it really depends on our label space and the retained set. This is just one way to guide our choice of theta, but this is not sufficient for us testing the model and evaluating this, right? Because we can choose one theta, but the problem is how do we evaluate this specific algorithm? Because we didn't optimize accuracy, right? If anything, accuracy will take a hit because we're forcing some of the examples to be predicted as uniform, but this is exactly what we can evaluate the algorithm on, right? Which is, what is the confidence distance? So what is here on the screen is the confidence distance that we're measuring, which is we are measuring how close the prediction of the network is to the uniform distribution over the forget set. And with that, before I'm going to present some empirical results and then talk a little bit more about the guarantees of this model. So here we did test the model in the following 4 data sets, where essentially each of the models is performing highly accurate other than in CIFAR 100, sorry, and with a baseline backbone of ResNet 18 and ResNet 50. And here are the baselines, right? So we have the pre-trained and the retrained. So pre-trained is the original model trained by the stakeholder, and then retrained is the retrained from scratch when we remove the data. then a synthetic baseline that was actually proposed by Kangwick, that is essentially getting random samples from the neighborhood, then labeled B, which is a standard algorithm, and this is compared with the proposed Pareto fine-tuning, which is algorithm 1. And what we can see is that it generally performed very well in these 3 datasets, but in the 4th dataset, the synthetic baseline and the labeled DP are kind of destroyed in the accuracy. And how do they do in the confidence? Well, in the confidence, it's what we would expect. The pre-train and the retrain, that they had no constraints on being uniform in the forget set, they have very high confidence on those. Now, the synthetic baseline, in most of the data sets, it does have low confidence simply because we sampled randomly from a neighborhood of the forget set point. But overall, it is destroyed in terms of accuracy in more complex data set, while the proposed method kind of works well in both the accuracy and in the confidence distance across all cases and models that we did try. And it also performs quite well, improving baselines on attacks, while one important note here, this is essentially something on the train set, right? Performance on the test set is rather similar. And here you can see similar results on the vision transformer backbone, where we see exactly the same story. There is a little bit of a reduction in the accuracy, which is reasonable if you go from the pre-trained to the proposed algorithm, but at the same time, we do get way better confidence, and lower confidence is better confidence here, which means that now, in principle, something in the forget set from CFAR 100, we are not able to confidently classify which of the 100 classes it belongs to, yeah? So the forget set is 100 instances, Muhammad, I think? Yeah, so 100 instances randomly, uniformly picked from the test set, sorry, the train set. And in fact, we do have an ablation in the paper showing what happens if you increase the number of samples in the forget set. And it is what you would predict, which is you're getting a hit, like especially when it comes close to it being more important than the retain set, you're getting a lot of hit in the accuracy, but the confidence is slightly better. Yeah.
That was a synthetic I was prepared. If you extract, not randomly, but the specific area, it was mixed, so I would say all the 8s, all the 9s, or something like that.
What do you mean extract?
Your delete set is the...
Your forget set is the whole class. So this is something that they do in unlearning, that in standard unlearning papers, they do want to forget certain classes. In our setting, I guess we didn't try this at all. Yeah, I'm curious what could happen, but we haven't tried.
Saying something like if you have 1,000 8s, delete the 900 of them and 8.
I mean, if I had to make a prediction, I would say that our algorithm would be better at deleting a whole class, right? Because simply when it sees that class, it just predicts uniform, which geometrically would mean that just deletes the boundaries from other classes in my mind. Now, if I just want to delete 90% of the class just instead of 100% of the class, I don't know. That's a good question. Yeah.
How robust
Amazing question. Can I answer in 1 second? Rob, did you have a question?
Just really kind of high level.
Yeah.
sounds like from the laws, we really would ideally have the retrain. That's sort of like following the letter. Just take that data out, retrain from scratch. That's kind of what the laws.
Yeah, yeah.
But what you're doing is very different generally.
Yeah.
From what that result.
Yeah.
I'm kind of just wondering, like, would this satisfy the law? Or like so different than what the law is asking?
The law is never saying, like this GDPR framework is never saying you should delete the models and retrain them. It just says delete the training data and their impact. So if you prove that you deleted their impact.
But I mean, anyway.
But that's a gray area.
I mean, again, we don't know what the retrain model would say, but I'm saying it's not saying the same thing. Even at the each set of them. And so it's not the same as. I'm just wondering, like.
So
it's something different or stronger. Even it's almost like you've obliterated anything model that is something.
So basically, this is a question that I think is related to one of the questions back there, which was saying that even if I retrain from scratch, nobody says that the prediction would be different, right? So imagine if I take we have a photo of my pizza plate in front of me, and I take a photo.
So what does the law want? Does it want to make sure that if I say delete my data, I have to make a prediction for things that are related to me? Is that what the law is asking? That's fine too.
Yeah, this is debatable at the moment, and I think it's playing out in courthouses around the world. I'm not a lawyer, as you know, so I don't know, but I think even Google at the moment is playing based on unlearning is defensible in the court, because that's, to my knowledge, like one of the person organizing that NeurIPS competition, she's in Google DeepMind, and actually it's Peter that is also a co-author here, is one of the collaborators. He was also in the NeurIPS competition. So basically, I think that's what they're playing out. I think it will play out in the courts if this is completely okay or not. I don't know. Manoli, yeah?
Going the previous slide. I want to rephrase a little bit in my mind what Rob says. The law says, I want to be able to check that when I delete the item, the impact has changed. And I am able to see a low confidence. Even that I know that in the retrain should be high confidence, someone can say, oh, that is the correct metric. Find out that actually you didn't delete, but you just try to adapt the training in order to convince me that I
sure.
Is that correct?
Yeah.
Okay, so okay.
Yeah, so that's absolutely correct. Yeah, but again, it's not in our context. It's not a violation. Yeah. No, you're absolutely correct. Someone can reverse engineer and find out from the confidence, oh, you changed the model locally there. And in fact, there is a more interesting question, which is like similar. So the law technically says delete the data. But what if I had a similar adversarial perturbation in epsilon ball around it? In principle, I deleted the data. But if I have like billions of data points, the law doesn't say delete all the nearby data points, right? So like the law has a lot of vague points that I guess will play out in the courts eventually. But all of this, like it brings back, right? So like even if the confidence is not low at this point, what if I do adversarial noise or Gaussian noise and I go to a nearby point that now has high confidence? Then I knew that you somehow played around or like did some fine tuning that messed up the prediction in that point locally.
That goes back to the question: if you delete the whole class, I asked before, if you delete the whole class and somehow the confidence go again super high class, how a signature that what you delete really impact the model. So my data,
Yeah.
as you said, you delete my data, but maybe all of my friends' data are very helpful to find out also my data and complete the manifold.
That's possible, yeah.
But if you achieve everything and the confidence goes high, it seems that somehow you find out also crucial attributes of the learning.
Yeah, exactly. And this is one of the things I really like in this line. It does, I always come up with new questions that are like, what happens in this case, in that case? Because, yeah, we've been doing decades of learning, but now how do we forget data? And to answer to the previous question, which is like, what does theta do? So we are currently running more ablations, I believe, or I want to believe. But essentially, this is one ablation on the simplest model of MIST, which shows what happens when theta varies from 0 to 1, right? Where if I go back a few slides, theta equal 0 would mean that I'm getting no uniformity. It's borderline the original model that we had, which has just high accuracy, and theta equals 1 means I don't care about the accuracy anymore. I just can predict uniform, right? So as we go from theta equals 0 to theta equals 1, there is some transition across models, right? So like it seems in NLP, ResNet, essentially logistic regression and certified logistic regression, in all of these cases, it seems that around 0.75, there is a like steeper gradient than before. And in the confidence, the story is a little bit more complex, but essentially this phase transition is not at the same point, but rather in 0.25, especially for bigger models, right? So for some reason, logistic regression is going down and then up and then down, which might be a byproduct of specific to MNIST. But other than that, like somehow in 0.25, most of these lines change, which is somehow reasonable that, you know, I need to go all the way up to 0.75 for me to obtain reasonable accuracy and reasonable uniformity. But this is the best result that we have at the moment in terms of like ablation. Yeah, Kanguk?
We got the
Yeah.
you're given the trees.
Mm-hmm.
They define the goals. And for
Mm-hmm.
a augment. Each
Okay.
Then like after training, and we got a model. And score the exact training set. So imagine having 0 training percent while high task accuracy. How should exposure by your definition for goal of unlearning? Whether you really need to use what you want.
But this model would be completely useless on the test set.
No, no,
Right.
still maintaining a static training set. Same training. Your third version of the training. A lost the measure the loss on that.
Mm-hmm.
Still like original training set. What else does still? It's randomly.
Yeah.
Another patch.
I don't know. We can try this. So right now, I don't have an answer on this. But it seems to me that if you, so if you so basically what you are trying to do is reverse engineer the objective with synthetic data. And I'm not very confident it would work, but we can try. It's not a guess here. We haven't tried this. So let me go on because we have like few minutes more. So the question is, what can we do about bounding this retained loss as theta changes, right? So like if we denote with alpha star the locally optimal retained loss for the retrained model, right? So we assume here retrained model again is the one trained from scratch with just the retained set data. And with alpha theta, the locally optimal retained loss of this Pareto fine-tuning model, then basically we need a couple of more assumptions which are pretty common in the literature, which is Lipschitzness of gradients and Hessians of our two losses. And then we, meaning Muhammad, can obtain a bound that is what you can see on the screen, which says essentially that these two are bounded by this, loosely bounded by this expression, where a lambda, if you remember from a couple of slides back, is the weighting hyperparameter for the L2 loss, right, the weight decay. C is the bound on the weights. Theta is the term that we are balancing the two losses, the uniform and the LA loss. And this expression means that we can obtain close to locally optimal retain loss from the retrained model as long as we make these be small. The problem with making them small is that now it creates different types of problems. And even if we do achieve this algorithm one does not have any certificate, right? So it has been the case in the robustness literature and the privacy literature the last few years, at least that I know, that certificates are quite important, right? So a company not only needs to unlearn or comply with the laws, but ideally they want to also have some formal certificate that they can say, okay, I did my best. And this is coming from the differential privacy guarantees, where one key notion there is that we have two neighboring datasets, the original dataset and the neighboring dataset D prime, that they differ in exactly one data point. And inspired by that, they have defined the certified unlearning, where the idea is that given a privacy budget, epsilon and delta, now the unlearning algorithm that takes in the training data set, the forget set, and the pre-trained model and returns the parameters, is essentially epsilon delta certified unlearning if using that unlearning algorithm results in us training in the retained set alone. And this is, again, background work. And what we did was try to extend this into our setting, which is if we have this G algorithm that takes in, again, the training set, the forget set, and the pre-trained model, how is this equivalent to us obtaining this Pareto-optimal model that consumes these two sets and returns the optimal parameters for this set? And we prove that this is possible in this specific type of privacy context, which, by the way, TTP stands for the attack that is test time privacy that we are studying. That we're studying in this work. And essentially, this is a part where I think we are kind of deriving a new algorithm, but it has stronger assumptions than previously. And these assumptions do relate with essentially the convex scheme that is required for making this. And this is, again, inspired by the differential privacy frameworks, where the idea is that we take these parameters W star, which are the parameters from the pre-trained model, and we want to bring these close to the parameters of the Pareto learner. And to achieve this, we can use Newton steps and Gaussian noise, inspired by the Gaussian noise on differential privacy. The problem is that to do this, to take the Newton step, we need the Hessian, and this has a lot of assumptions, again, that we have a strongly convex model, but in our case, we can bypass this by assuming some ellipsisness, because inverse Hessian is not very easy to compute, and essentially design a model that can estimate the Hessian even for larger models. But for this to work, lambda should be rather small. And unfortunately, this algorithm too, even though it provides some certificates, it's rather finicky to work with. So we only have some experiments on smaller mixed logistic regression results. But in those experiments, it does seem to work relatively close to algorithm 1, with the additional benefit that it does provide some official certificate of this unlearning. And with that, let me conclude, because I think we're due. Basically, what we introduced here is one method for studying this test time privacy, which the idea is, can I induce the maximum uncertainty over these forget set instances, such that, for instance, a model provider or a law enforcement agency or anybody querying the data that I wanted to be deleted cannot anymore make a confident prediction? And the answer was yes, and algorithm 1 and 2 can provide this. Especially algorithm 1 is model agnostic, and we showed results on ResNet and Vision Transformer. And we do have in the paper one algorithm also for the online setting, which was one of the questions before. Do I assume all the forget set is coming at once? No, sometimes it might be coming sequentially. So we do have some guarantees for that as well. And there are a lot of interesting questions from the audience as well, but some of these that I have put down is, of course, a Hessian-free algorithm for algorithm 2 with a certificate would be the best. And applying this to discrete type of data, right? So we assumed images, so continuous type of data. And essentially all of these attacks, where there was one question there about a stronger attack, yeah, of course there will be stronger attacks that will be relevant. And with that, thank you very much for your attention. By the way, this is GPT-5 is getting a lot of things correct, but I love how Bucky has human hands now. So yeah, Kanguk?
It's related to the in this case, I guess, where either is unlearning. Imagine if you have a single data point, carefully designed of your whole tree, the data points. Then if you consider the unlearning of those data, who isn't participating, and come up unlearning should be not only effective, should be evident. That goes back to our discussion, where like need to just pattern or really want to ask what is the component of reason data. I need to hear about that.
So we're still being recorded. So I'm gonna say this method does not induce any guarantees about the neighborhood, but we did try, if the attack like if you apply a PGD attack with few steps, it should be fine still in the neighborhood. But like if you make it super, super effective, or like I imagine if you design an attack that is more powerful than the PGD attacks from the adversarial, like the robustness literature, that yeah, you could find something in the epsilon ball that essentially still has high confidence. So basically, it should be possible for you to find a point within that epsilon ball that you didn't fix. But fixing that point would be super hard, right? Because now if I impose, even if I fixed it for the whole epsilon ball, I imagine that in that epsilon ball, if I'm unlucky, there would be another point that is not in the forget set, and I need now not to patch that while to patch the other one. So we have this conflicting point, number one, which I think is unsolvable. And number two, if I make epsilon big enough, I cover the whole space anyway. So this is not a solvable problem, I think. But it is a very good question. It is a very good question, and I don't know how to solve it, honestly. And we don't have any guarantee here about the epsilon ball. And you're absolutely correct. If I patch the point, and now I rotate the image, problem not solved. Yeah, I'm with you. Yeah.